Good morning, everybody. I hope everybody's doing well. It's your, what is it, day before spring break. It's pretty nice. Um, so today's lecture will cover not all of, but some of section 11.3. And just to let you know, I will not be holding office hours today because I'm leaving town. And so I have to kind of put things together before I rush away. So, um, yeah, that's just a heads up that I will not be doing office hours just today. It's kind of a random oddity, but still, today's going to be kind of an okay day as far as content because the integral test, which is section 11.3, is generally speaking a good, easy test to kind of get used to. And mainly because we have just recently finished 7.8, which is, again, the reason why I do chapter 11 after 7 is because of stuff like this. Your recency with the material for improper integrals and the comparison tests for integration for improper integrals ends up being very useful here. Also, I should say the last 2 or 3 days, my internet has sucked. So if I cut out a few times, I apologize. There's just not really much I could do about that right now. I don't know why the last 2 or 3 days has been like that. I've turned off everything I possibly can and reset my router and all that fun stuff. But what are you going to do? So I hope I come through loud and clear. And sorry, that's my mic stand that I'm moving. Anyhow, you can see that at the top of this section, I wrote these 3 paragraphs here. We now know that given a geometric series, and I wrote that actually in slightly different form, right? Normally you see a geometric series, and man, I have to wait quite some time. I actually have zoomed in on my laptop, and it's taken 10 seconds for that to happen on my desktop. Interesting. Anyway, so the way we've seen this series summation in the past, and actually in your pre-calculus course, is like this. You would have a sum, and you'll have to be patient while my ink catches up with my words, from n equals 1 to infinity of a times r to the n minus 1. I'm telling you right now that that is identical to this down here, because notice both series start with the power of 0. So they are technically the same series. If you were to expand this series out, you'd have a times r to the 1 minus 1, or r to the 0th, plus a times r to the 2 minus 1, which is r to the 1st, plus a times r to the 3 minus 1, which is r squared, and so on and so forth. Whereas the series down here, if you let n equal 0, you have a times r to the 0th, plus now let n equal 1, a times r to the 1st, plus now let r equal 2, right? So you can see that it is actually the same series. It's just indexed differently than the series that you're used to. I actually strongly prefer the notation down below there, the n equals 0 to infinity. It just kind of matches with my brain a little bit better, but the idea is still the same in both cases. The very first term in your expansion should have a power of 0 on your common ratio. All right, that being said, let's go ahead and read the rest of this. I'm going to zoom out. I'm going to wait for my screen to catch up to me. So I will pause. Do, 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 do. You can see how slow my internet is. Okay. All right, so we now know that a given geometric series can be, given a geometric series, we can determine convergence or divergence based on the value of the common ratio. If convergent, in other words, if the common ratio in magnitude is less than 1, we can even state that the series converges to a over 1 minus r. I cannot say enough how rare it is to find the exact value of a series, at least so quickly. You can actually find some values of series, but geometric series is really, those are the series you want to work with, because those are the ones you can actually not only determine convergence very easily, but determine what it converges to. Now, what if our series is not geometric? There are more non-geometric series than geometric, and that should be somewhat obvious to you. So it would be nice to determine the convergence or divergence of these series. And we have encountered some very special series, such as telescoping series. However, those are also incredibly rare. And if you don't remember what a telescoping series is, it's that series where when you add terms, I'm just going to write it like this. I'm just making one up. Give it a moment while my screen catches up to me. I hope at least my audio is not cutting out as much as my video takes forever. Maybe I can see if I can reboot my router again. Let me just double check. You guys just hang tight for a moment while I check something in the background. You can hear me clicking away here. There we go. Let's see, top. The audio seems just fine. Okay, so I'll just continue and hopefully we can all suffer through it today. Right? Just means it's a much more easygoing lecture today. Right? So let's take a look at this series. I'm going to go ahead and say this series is not going to start at 0 because then I'd have division by 0 initially. So let's just say our series starts at 1. Actually, let's play a little game. Let's suppose this series doesn't start at 1. Let's suppose it starts at 10 and goes to infinity. It doesn't. I'm just doing this because I want you to know not all series have to start at an index of 1. And the convergence or divergence of the series does not actually depend on the first finite number of terms. You could throw out the first billion terms and still determine whether a series converges or diverges. So this is an example of a telescoping series because if you were to add up the terms, that's 1/10. Well, if you let n equal 10, it's 1 over 10 minus 1 over 11. And then you add the next term in. The next term, when you let n equal 11, you would have plus 1 over 11 minus 1 over 12. The next term in line is when you let n equal 12, and that would mean you're adding 1 over 12 and subtracting 1 over 13, and so on and so forth down the line. I'll just put plus ... You can see that as time goes on, the very first term you always keep at 1/10. However, everything else gets canceled out. In fact, almost everything else, except for if we were to stop at, let's just pretend instead of going to summing up to infinity, let's pretend that we're summing up to some value of k. Let's just pretend. Then you would sum all these values up from n equals 10 to n equals 11, waiting for my screen. Come on. There we go. It's at n equals 12, and so on and so forth down the line until you get to n equals, what did I say, k? So at n equals k, you would have 1 over k minus 1 over k plus 1. But remember, the 1 over k actually has a term right before it that'll cancel with it. And so in the end, this series will compress down to the first term minus, waiting for my screen, the last term. Let's wait there. Good. And if you then say, well, you know what, I'm not going to stop at just k, I'm zooming out, waiting for my screen. This is part of the problem of living in the sticks. It's a good time to just sip a cup of coffee or something like that. All right. So if we were to allow k to wander off to infinity, well, that would mean that this last term here in our summation would wander off to 1 over infinity, which is 0. It will tend to 0. And so over the long haul, if you were to add up all the terms of this series, it would end up just being 1/10. Okay. That's, again, just a reminder of a telescoping series. I like to every once in a while slow down so that you guys can recall a few kind of key uh, elements of what we're going through. And sequences and series, I really do like to take my time at certain points just so that we really try to cement topics down. I want you guys to be awesome with this stuff so that when you get into your next course, whether it be an engineering course or differential equations or Calc 3, that you are supremely confident with your sequences and series. Anyhow, so turns out that telescoping series and geometric series, we can determine what those actually converge to pretty easily. However, everything else, it's all bets are off. And we do have a brand new test, which is called the divergence test. And that will help us with most other series to determine if they diverge, but it doesn't tell us anything about convergence. So you cannot use the divergence test to tell me, oh, this converges by the divergence test. There's no such thing. So I'm going to write that down in a moment, but I'll go ahead and read this last paragraph. Our only real general test for any type of series is the divergence test. Now we begin to explore a new method to determine the convergence or divergence of series satisfying very special conditions. And in fact, every section from this point forward, we're going to say, well, if your series has this set of special conditions, then here's a test you can use to determine whether that series might converge or might diverge. So we start getting into these weeds at this point. If you have a very special series, maybe you can determine it converges or diverges using a special test we're going to invent here. It's important to note that the tests we encounter from this point forward will not yield a value for convergence, but rather just allow us to determine whether a series converges. So it will not tell us the value of the series. It's not like a telescoping series or a geometric series. All the rest of these tests are going to do for us is tell us whether the actual series we've been handed will actually converge or actually diverge. So that's an important statement I just want you to think about. Now, before we leave this page, I do want to write on here my warning just a moment ago. So let me go ahead and zoom in a little bit. And my handwriting or my video will catch up to my handwriting in a moment, so it's okay. So I'm going to put in here a warning. The divergence test oh, good, it is keeping up with me. Which, by the way, the divergence test is the following. I'll put this in little brackets. If the limit as n goes to infinity, it's like everybody's favorite test, really. If the limit as n goes to infinity of our sequence is non-zero, then the summation n equals 1 to infinity. Actually, it doesn't have to start at 1. It could start at anything. I'll say n equals k to infinity of our sequence will diverge. So the series summation k equals to infinity of a sub n diverges. That's the divergence test. The divergence test will only tell us whether or not, well, whether, I'll say not the whether or not, will only tell us if a series diverges. Again, you cannot use the divergence test to show convergence. To show convergence. Just a little warning there, because I do find that students tend to do that. They say like, oh, this converges by the divergence test. First of all, that sounds weird, right? It converges by the divergence test. Like it's just an oxymoron. But so just don't do that. Don't use the divergence test to show anything other than divergence. I just want to also mention thank you very much for showing up the day before spring break. You guys are awesome. I notice right now that we have quite a few people in, almost the entire class, 20 people in. So that's great. You guys are awesome. I'm cheerleading for you. Rah, rah. You guys are great. All right. So let's go ahead and pop forward and introduce ourselves to a brand new type of series. So far, we have geometric series and we have telescoping series. Also, from your stint with pre-calculus, you probably have seen arithmetic series, but we don't actually touch upon those in Calc 2, so don't worry about that. All right. The harmonic series is a very, very literally unique series in that it's not like, oh, I have a harmonic series. It's of this form. No, this is literally, this guy right here is literally the harmonic series. So when I say, oh, we have a harmonic series, I literally mean it's a summation from 1 to infinity of 1 over n. That is called the harmonic series. And you can see if you were to allow n to equal 1, you'd get 1. N equals 2, you get 1 over 2. N equals 3, you get 1 over 3, and so on and so forth down the line. Now, a lot of people will say, oh, this converges because because 1 over n tends to 0 as n goes to infinity. I'm going to again just remind you, just because the limit as n goes to infinity of 1 over n equals 0, let me try my English here. Just because of this, that's probably not the right way to say it. Let's just say despite the fact that the limit, there we go. Despite the fact that the limit as n goes to infinity of 1 over n approaches 0, we cannot say anything about the convergence or divergence of the summation n equals 1 to infinity of 1 over n. So I just want to remind you about that it's the other way around. If that limit is there we go. If that limit was not 0, I could tell you by the divergence test, the summation of the sequence 1 over n would diverge. That would be true. If that sequence was, if the sum of that, or I'm sorry, the limit of that sequence is non-zero, then basically as time goes on, I'm adding something that's not 0 over and over infinitely many times. So obviously that summation will diverge. But just because this limits to 0, that says nothing about the summation of the sequence, or the sum, if you want to call it that. Okay. So let's go ahead and see or investigate the convergence or divergence of the harmonic series. It's a very, very, very important series in Calc 2 and future courses, but pretty much Calc 2. The harmonic series, here's the theorem, is divergent. Even though the sequence 1 over n will tend to 0, you would think that means, that if you sum up a bunch of things that are tending to 0 as time goes on, it will converge. Nope, it doesn't. It diverges. And we've seen something like this. Remember, this is not I'll do the proof in a moment, but as an aside, I'll do this in blue. If you wonder why I sound so awake right now, I've been up since 3 a.m. Crazy, right? So the aside here is recall the integral from 1 to infinity of 1 over x to the p power. That improper integral diverges if p is less than or equal to 1. If the power on x is less than or equal to 1. So more specifically, the integral from 1 to infinity of 1 over x to the first diverges. So this is the same idea that, because really, if you think about it, the area under 1 over x from 1 to infinity is very, very similar to the summation of 1 over n from 1 to infinity. And so let's actually start the proof to show that. Okay. So I'm going to, in fact, take my time with this because it's early morning. It's nice to not rush through things every once in a while. I know I tend to rush. I apologize. It's just a habit, a really bad habit of mine. I know that. So here's an x-axis. And let me go ahead and throw in here a y-axis. Throw this all the way over here if I want to. There's my y-axis. I don't need to be super exact with this, but I am going to try my best to graph in here a 1 over x. So I'm just going to go ahead and draw that in right now. Turn off my ruler. Let's pretend this is x equals 1. And so therefore, this must be a height of 1. And if you wonder where I'm, oh, it has caught up to me. Okay, good. So, and then 1 over x, if I were to graph it, let me use a different pen for that. Let me use green. You can hear my pen on my tablet here. Well, let's see. And at x equals 2, it's a height of 1/2. Keep going here. And at x equals 3, it's a height of 1/3. So I don't know, somewhere around here maybe. And you get the idea because you guys have been graphing for years. So I'm just going to stop at that point and just say it continues forward. Now we know from our topics in improper integration that the area underneath this curve from 1 to infinity will diverge. So let me go ahead and erase all this stuff starting at 0 and instead start at 1. So let's go ahead and take a look at some rectangles. In fact, maybe I should put x equals 4 in here just so that I can really showcase something. All right. If the area underneath that curve is infinite from 1 to infinity, and that's not an if, we happen to know that's true. Off to the right-hand side, we've actually proven that. Imagine that I tried to approximate the area underneath this curve using rectangles, just like we have in the past. But instead of doing like delta x's of being super thin delta x's, I'm going to be using delta x's of size 1. So in other words, my rectangles that I'm going to be placing in here will have width of 1. And I'm going to use left endpoints as well. So let me showcase that. I'm going to use red for my rectangles. I hope you would agree that this is an approximation. If I continue this on forever, this is an approximation for the area underneath the curve 1 over x. Okay, so let me write that down. The integral from 1 to infinity of 1 over x dx can be approximated by adding up the areas of these red boxes. Of course, I don't mean just those 3 red boxes. I mean those red boxes if we continue to draw them onto infinity. So I'll just say off to infinity. I hope you're okay with that. So great. But one thing you should note here, very easy to see, is that area, because this is that green curve 1 over x is a decreasing function and we use left endpoint method, that area of those boxes is going to actually be greater than the area underneath that green curve y equals 1 over x. So let me just say moreover, since y equals 1 over x is decreasing, We can see that in our drawing. Okay. Since y equals 1 over x is decreasing and we are using left endpoints, I don't need to capitalize the word left. The area of the rectangles is greater than the integral from 1 to infinity of 1 over x dx. Well, if the area of those rectangles is greater than the area underneath the curve, and that's easily seen there, just incredibly easy to see that, then, and we also know that the area underneath the curve 1 over x from 1 to infinity is infinite, that implies the area of those rectangles, and I know my English here is not the best, I'm just saying the area underneath all of the sum of all those rectangles, must be infinite. Now, what does this have to do with the series that we're dealing with? Well, if you take a look at our series, the harmonic series is this, the summation n equals 1 to infinity of 1 over n. That's the harmonic series. Waiting for my pen to catch up. There we go. Well, that's 1 plus 1/2 plus 1/3 plus dot, dot, dot. Well, if you look at these rectangles, the area of this first rectangle is 1. It's a 1 by 1 area. The next area is a 1 by 1/2. It's a width of 1, a height of 1/2. The next one is a 1 by 1/3. That is, the area underneath those rectangles is actually the harmonic series. It's 1 plus 1/2 plus 1/3 plus 1/4. So let me go ahead and write that down. But the area of under those rectangles is 1 plus 1/2 plus 1/3 plus so on and so forth on to infinity, which is the summation n equals 1 to infinity of 1 over n, which implies, by the way, that's the harmonic series. So that implies the harmonic series is divergent. QED. All right. So there we go. We now have a pretty strong proof. That's a really convincing proof that the area underneath, or I should say that the harmonic series diverges, because if you add up all those boxes, which is the harmonic series, it is bigger than or greater than the area underneath the curve 1 to infinity from 1 to infinity of 1 over x. And we know the area underneath 1 over x from 1 to infinity diverges. So bam, not too bad. Now, I would love to tell you that we're totally going to use that, but we're not. We are, okay. It'll sneak itself into problems. Like you start QED, by the way, somebody's asking right now. QED is quod erat demonstratum. Quod erat demonstratum. It means so it has been proven. It's Latin. Usually, good proofs are finished with the QED. There's actually a book called QED. Not that that's where it was invented. This is traditionally how proofs were finished off as QED. So it's just a fancy way of saying in your face, mic drop, that type of thing. They didn't have mics back then, so there you go. Otherwise, they'd say mic drop. So anyhow, let's see. You will run into harmonic series, and they'll be mixed into other problems. So whenever you see a summation of 1 over n, you can just pretty much say, all right, great. That likely diverges. There are exceptions. Here's a great exception we just saw. So I'll put this as a warning. Warning. Just because I hate that I start sentences like that, just because. So maybe I should say, how do I want to say that? A series. There goes.
Sorry, I didn't quite catch that.
See what happens? See what happens? No.
Okay.
You can't help it when you're teaching this material. Let me put this away. Let me hide her somewhere. In a drawer. All right. So, a series involving 1 over n need not diverge. So, for example, we just had a series not too long ago, n equals 1 to infinity, of 1 over n minus 1 over n plus 1. That series does involve 1 over n, doesn't it? And yet, that was a series that we found would be, I think we started at 10, didn't we? So that was a series we found converges to 1/10. So even though this has a 1 over n in it, the reality is that if you write out a few terms, you'll find that the 1 over n plus 1 starts canceling that 1 over n as time goes on. And so don't just think, oh, I have a 1 over n, therefore it diverges. No, that's not true. This is not just 1 over n. It's a 1 over n minus a 1 over n plus 1. If you pulled these apart, it is possible, and in fact, it is true, if you pulled these apart, that one of them does diverge. Actually, they both diverge if you pull them apart. But when you glue them together, they provide us with a convergent series. So this comes back to your limit laws back from Calc 1, that if in Calc 1, if you had a limit, let's just pretend as n goes to infinity of, I don't know, let's say n, actually Calc 1 was x's, so let's do x times x e to the negative x. Just because that x goes off to infinity does not mean this whole stupid thing goes off to infinity. In fact, it doesn't. This thing goes to 0. So pulling this apart is not legal because when you try to pull it apart like this, one of these limits is not finite. That's just a recall from your Calc 1 class. You cannot break them apart and say, oh, well, one's not finite, so the whole thing is not finite. That's not true. This limit is actually 0. And so just to let you know, these like sums basically work like limit laws. If you pull that summation apart and one piece diverges, then you have to glue it back together and try something else. It's a really hard thing, I think, for most people to digest. So if you feel confused about that, you're not alone. That is, generally speaking, a very tough thing for people to grasp. When in doubt, if you can go ahead and try to break it apart, but if one piece diverges, then you have to glue it back together and do something else. Okay, that's just a good idea, right? However, by itself, if somebody just handed you the harmonic series, this guy right here, I'll wait for my screen to catch up, which might be a few minutes. Who knows? All right, by itself, if somebody just hands me that, I easily know that that diverges because it's the harmonic series by itself. That's the key, by itself. Okay? So just weird little things with series. There's going to be some very obscure, cool things that happen as we move forward that that will blow your mind. Honestly, there are some really interesting things about series. But all right, So let's move into the next subsection, which is actually what this section is all about. 11.3 is all about this new test called the integral test. And this is going to be, it's kind of like, you know what this integral test is kind of like in my brain? It's kind of like by parts integration, in that it's the first newer method that we learned in this course to integrate a function, or a product of functions in that case. But it's somewhat clunky. It's like, for me, always a last ditch effort. It's the very last thing I want to grab is integration by parts. I'll do anything else before I do integration by parts personally. I don't want you to think that. You choose what works for you. But for me, integration by parts is my very last tactic. It's still a very powerful tactic. Same thing for when I want to determine whether a series converges or diverges. The integral test that we're about to introduce is my very last tactic, mainly because it's just a bit of a mess. It's kind of a messy tactic to use. All right. But still, it's a good a starter tactic, and it has its strengths. It can be used in some very unique and interesting situations, but there are some major conditions. So let's talk about this. The integral test. Suppose, first of all, you're handed a series. Okay. So this theorem could have been written better, by the way. Suppose you've been handed a series and you can exchange the sequence in your series. So this guy right here, you've been handed this series. You can exchange your sequence, a sub n, for f of x. So we're going to suppose, SPS to me always means suppose, that a sub n is equal to f of n. In other words, you have some background function. I'm waiting for my screen to catch up to my handwriting. There we go. So you have some background function that mimics your sequence for the natural numbers. As an example, if you don't know what I'm saying here, suppose that you had a summation n equals 1 to infinity of, I don't know, let's say 1 over e to the x. Okay. And what I would do, or it says 1 over e to the n, actually. One thing that you should note here is if f of x is equal to 1 over e to the x, then whenever I have a natural number I plug in, it's the same thing as a sub n, where a sub n is this sequence right here. Okay. So basically, I'm just exchanging x's for n's. Okay. So that's all I mean when I say that we start with a series. I decide to trade it out for a function. Now remember, functions are functions of continuous variables. X is continuous variable, whereas n is discrete. Not a big deal, just letting you know. All right, so let's go to the theorem. Suppose that we have a function. I'm waiting for my screen to catch up. Tick tock. There we go. Suppose that we have a function. There are, I should say, 3 very important conditions. We require that our function is continuous. I would say 1 over e to the x is continuous. We require that our function is positive. I would say 1 over e to the x is definitely positive. And we require that our function is decreasing. All 3 conditions have to be met for you to use this theorem. But if you can do that, then the convergence of the improper integral will imply convergence of the series. The divergence of the improper integral implies divergence of the series. Let me write this down in a clean form, because this is the actual theorem, but I sometimes like to reword them a little bit so that so you can wrap your mind around it. So ignore my note for a moment. I'm going to go down here. I'm going to say, given the summation n equals, I don't have to start it at 1, so I hope you don't mind. I'm going to go from k to infinity of a sub n. If we let f of x equal a sub x, I guess. It's a terrible notation, but the idea is that you basically exchange your sequence for a function of x. Okay. So please forgive my horrible notation, but there you go. If one, f is continuous, two, f is positive, and three, f is decreasing. If all three of those conditions are met, then the convergence or divergence of the improper integral k to infinity of f of x dx implies the convergence or divergence of the summation n equals k to infinity of a sub n. So basically, I can, instead of evaluating the series, I could just say, let me look at the improper integral version of that series, essentially. These three conditions are critical. The continuity, you could just say, I mean, it's pretty easy to say, like, oh, e to the x is continuous, right? So that, you don't have to prove it. You just have to tell me this is continuous. You do have to kind of showcase that your function is positive. Generally speaking, it'll be very much like, well, 1 over e to the x is positive. What do you want me to say? It's just positive. It totally is. So I'm fine with you saying that. But the very last one, this guy right I'll do red here. This very last one right here, I would remember our discussion in section 11.1, actually, when we talked about a monotonic bounded sequence being convergent. I had said to you, if you read the textbook, the author will show that a sequence is monotonic by looking at a sub n and comparing it to a sub n plus 1. And I told you at the time, that method, while it can work at times, is usually a terrible method. Instead, look at the derivative, right? Just look at the derivative of your function. If it's always negative, then yes, your function's decreasing. You want f prime to be negative because that would imply your function's decreasing. So that's the only thing that you really do have to actually do some long-winded handwriting for. Nothing terrible. Just take a derivative and show that that derivative is negative. But once you have those three conditions met, check, 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 then integrate using the improper integral. And if you find that that integral converges, then the related series will converge. So really, really beautiful method. It's not a method I prefer, but it's a beautiful method. Okay. Oh, by the way, just thought of it, kind of random that I'm thinking about this right now. The integration B this year is held at the end of April. So we have about a month until that day comes. We still haven't decided on an exact date yet. I think it's like the last Friday in April. So giving you a heads up, I'll tell you more as I find out. I'll probably find something out over spring break. So I'll probably send out like a news item email. And Samuel's asking, does the series converge to the same number? No, that's a great question, Samuel. No. And by the way, thank you for participating and being awake, right? Because it's hard for me. I'm not sitting in front of you in a classroom, where you're, paying close attention. Like some people just turn this on and walk away and come my office hours, their computer's still on, but they're not around, that type of thing. Thank you very much for participating. I appreciate that. But no. So one thing that I want to remind you of is one of the statements I made right at the very beginning, which is that, and I'll highlight it as I say it here. I'll wait for my ink to catch up. So my page will catch up to me. There we go. It is important to note that the tests we will encounter from this point forward will not yield a value for convergence, but rather just allow us to determine whether a series converges. So this will not say what the series will converge to. It'll just tell us that it converges, mainly because the area underneath the boxes, if you think of it that way, because that's really what happens when you're using the integral test, is you're creating these boxes. Wait for my screen to catch up to my words. Tick tock, tick tock. Well, there we go. So we did something like an integral test when I proved the divergence of the harmonic series. That was actually, I was actually using the integral test to do that. But the idea is the area under those boxes is not the same as the area underneath the curve. The area underneath those boxes specifically is larger, not the same as, but larger. And if the area underneath that curve converged, the area underneath those boxes would be smaller. They wouldn't be the same. They would actually be smaller. So the answer to your question, long-winded as it may sound, is that no. The value that the improper integral converges to is not the same as the value of the series that it converges to. I was trying to build the language there, sorry, but they're not the same number. Yeah. The next natural question is, well, then how do we find what it converges to? And the answer is you don't. You just don't. So this starts that area of mathematics, which is probably one of the more important areas of mathematics, which is that we want to know that something exists. We don't know what its value is. We just want to know, if I'm going to put the effort in to build this bridge, I need to know from the beginning, will this bridge actually hold together? If I try to do the mathematics and find out there's no way to make the bridge hold together, there's no point in me building it, right? And that's kind of the idea here is, if there's no solution to this weird problem that you're working on, why even start? That's the idea. Okay. And by the way, my little note here says, technically, it's okay for the function to be non-positive or increasing. So notice our three conditions here. I'll write them as 1, 2, and 3. Wait for my screen to catch up. Waiting. Come on. Oh, there we go. Ein, zwei, drei. Okay. So those three conditions that we need: continuity, positivity, and that our function has to be decreasing, those actually don't have to always hold. Remember, when you're trying to determine whether a series converges or diverges, I've repeatedly said that you could throw out the first 1,000 or billion terms of the series, because the fact is the convergence or divergence of the series does not matter or doesn't depend upon the first billion terms. It depends upon the remaining infinite number of terms. And so if you have a function that you want to work with that is the same as your series values, but your function is initially increasing, or it's initially negative, or it's not even continuous initially, well, wait until it is positive, decreasing, and continuous, and work from that point forward. Because again, I could throw out the first billion terms. So the point of this statement is, it's totally okay for your function that you're going to compare with, that function is initially not positive or increasing. That's totally fine, just so long as after some point it is decreasing and positive. I hope that makes sense. You can just throw out the first 3 billion terms or whatever it is. It seems so weird that you just throw out chunks of mathematics, but in reality, we're not concerned about the value. We're concerned about the convergence or divergence, and that only concerns the infinitely long end behavior. You can tell by my fervor in my voice that I really dig this stuff. This stuff is just, to me, pretty neat. Of course, I love mathematics. That's just how it is. So, all right, let's go ahead and try our hand. at one of these problems. And I highly recommend, I haven't said it enough, but I highly recommend that you like take your time and try and attempt these problems, especially while I'm talking or something like that. Attempt these problems off to the side. Just think about what you would do here and think about how you would tackle these. In a classroom, I would poll the classroom and I would sit here and we'd have conversations and everything. But unfortunately, in an online environment, I'm just sitting in a room and there's crickets around me. So that's just how it works. All right. So determine if this series is convergent or divergent. Notice the words that are missing from this. The words that we've seen, the secondary sentence that we've seen in all other problems is if it converges, find its value. You will not see that from this point forward because you won't be able to find its value. That's just it. If it converges, you still will not be able to find its value. So think about the methods we've learned so far. I'm going to write them down. So I treat this just like I would treat integration techniques. I start listing out our techniques. So the very first technique that we dealt with when we are talking about convergence or divergence of a series is to ask, is it geometric? Because if it is geometric, I can determine whether it converges or diverges pretty easily. And just so that nobody makes the mistake, there's one very easy way to determine whether a series is geometric or not. If your series is of the form something, I don't really care what, it doesn't actually have to be a number, I'll just write something to the nth power. And if you take a look at that series, it's not something to the nth power. It's got a second power, but that's not an nth power. And anyway, it has a term that's not even to a power. So, well, it's only to the first power. So it's definitely not geometric. The only other type of series that we've been able to possibly determine convergence or divergence for is the telescoping series. They're so rare that I don't even bother writing that down. They're incredibly rare, but you can tell that you have a telescoping series if you have a difference of a couple of terms, or you might have like a logarithm, which you have here, but it would be two logarithms. So that's kind of hard to talk about without drawing out like a dozen examples. So I'm not going to worry about that right now. But let's see. One other thing that we could do here, divergence test. Again, I'm not just asking, is it convergent? I'm asking, is it convergent or divergent? So it's always worthwhile to ask, will the divergence test help out here? And I do think that it's important for me to just try it here because I need to showcase when the divergence test doesn't work. So divergence test says, take the limit of the sequence that this series is based upon. Limit as n goes to infinity of 1 over n times the natural log of n being squared. Well, we know very easily that as n goes to infinity, that is 0. And because that limit is 0, the divergence test says nothing. I'm going to write this. It's inconclusive. That means inconclusive means that divergence test is not telling me that this diverges. It also doesn't tell me it converges. It just says I can't say anything. If that limit was non-zero, yeah, that's totally conclusive. That means that the summation would diverge. So our only two major tests so far fail. So what are we going to do? Well, the next tactic would be the integral test, or sometimes I call it the integral comparison test, but we'll just call it the integral test. So I'll write that down, integral test. Oops. I'll zoom in here. All right. So the integral test. What are you going to do? Well, you're going to let f of x be the same thing as your sequence, but with x's. So it's going to be 1 over x times the quantity natural log of x, and this is to the second power. Now I need to make sure all three conditions to use the integral test are satisfied. That unlocks the door so I can start using the integral test. I can't even touch the integral test until I showcase all three of those conditions are met. And those three conditions are continuity, basically, eventually, positivity, again, eventually, and decreasing, again, eventually. So let's see. F is continuous. It actually is continuous, and that's pretty much all you have to say. It's continuous on, let's see, 1 to infinity, right? You would think 0, right? Most people would say, wait, no, it's only at 0 that I have a discontinuity. But actually, the natural log of 1 is 0. So as long as I start after 1, I have continuity, because natural log is continuous, x is continuous after 1. So there we go. So that's all I need. There's no proof. I don't need to prove anything there. So I don't want you to think that you have to go through some rigorous proof of showcasing something's continuous. Like I said earlier, continuity and positivity are more just statements. Although I did mention the interval on which it's continuous, just because it was easy. Also, F is positive. Check. Notice I didn't go into telling you why, because it's kind of simple. And if you're working on an exam, I don't want you to sit here and say, well, okay, that's numerator is +1. The denominator, let's see, the x's are positive because we're going from 2 to infinity. And this is a square. And so whenever you square something, it's positive. So F is positive. The reality is you are well beyond that. I know you know that. So it's okay to just tell me it's positive, but you have to tell me it's positive. You can't just not say it. It is a requirement. So this is the first, and this is the second condition. Now we have to worry about the third, and the third you are going to prove. The third, I want to showcase that it's decreasing. I need continuity, positivity, and I need to show that this function's decreasing. So f prime of x. Well, here we go. The quotient rule. Derivative of the numerator is 0 minus, right? Because it's derivative of the numerator times the denominator. Okay, great. Minus the numerator times the derivative of the denominator. The derivative of that denominator, that is a product rule with a chain rule as well. So let's go ahead and take that derivative. Derivative of x is 1 times the natural log of x being squared, plus, now it's going to be x times the derivative of the natural log of x being squared, and that's a chain rule. The natural log of x, the derivative of the natural log of x squared is 2 times that natural log of x to the first power times, by the chain rule, 1 over x. And this is all over this denominator squared. So that'll just be x squared and then natural log of x raised to the 4th power. You may think like this looks terrible. Oh my gosh, we'll never be able to do it. But it actually is not bad. We can quickly clean this up. Leave that negative on the outside. I think it's just a good idea because you want to showcase eventually that this derivative is negative. Let's see, x's cancel. So we have plus 2 natural log of x. And this is all over x squared. Natural log to the 3rd power of x, 4th power, sorry. I already did my mathematics. And notice through the numerator and denominator, natural logs do cancel. So this is going to be the negative natural log of x plus 2 all over x squared natural log cubed of x. And this is definitely, what I'm circling up is positive, and there's a negative in front of it. So that is definitely a negative number. Wouldn't the function not be continuous because in natural log of 1 is, no. That's what I said. It's continuous on 1 to infinity, right? So when I said that it's continuous, I specifically said it's being asked privately to me, but the question is, wouldn't the function not be continuous because the natural log of 1 is 0? and it'd be undefined. And I'm saying that f is continuous from 1 onward, or from on the interval 1 to infinity, the open interval, not at 1. Notice that open interval doesn't include 1. It's everything after 1. And by the way, if that concerns you, note the problem, zooming out here, doesn't start at 1 anyway. It starts at 2. So I could actually say f is continuous on 2 to infinity, right? So really, you don't actually have to worry about that. Not in this problem. We're starting at 2. We're not really starting at 1 anyway. Okay. I hope that helped out. All right. So back to the derivative. I hope you can see that this is that circled expression is going to be positive, but there's a negative in front of it. So this is less than 0. And because that's less than 0, that means that f is decreasing, because that's the derivative of f. So we have continuity, positivity, and we have that f is decreasing. We have unlocked the door, so now we can use the integral test. All of that was just to start using the integral test. Now we can actually use it. So let's go ahead and engage the integral test. We'll take the integral from 2 to infinity, because that's what our summation was going from 2 to infinity, of 1 over x times the natural log squared of x dx. And I'll just do a u sub from the get-go. Let u equal natural log of x, so that du steals away a 1 over x dx. If you do that, the integral will actually go from, let's see, when x is 2, we have u is going to be the natural log of 2. And when x runs off to infinity, well, u runs off to infinity as well. And this is going to be 1 over, remember, I'm stealing away a 1 over x dx, and I'm trading that out for a du. And the natural log gets traded out for a u. So we have a u squared downstairs. And now I can actually go ahead and say this is the same thing as the limit as t runs off to infinity. Remember, I have to use limits when I'm dealing with improper integrals. Most people did great with that on the exam, by the way. Of the integral from natural log of 2 to t of u to the negative 2 du. Actually, what am I talking about? Let's just stop. The reason why I can stop is because what do we know about this integral right here? If the power is 2, if the power is greater than 1, we know it converges. Yeah, so there's no need for me to actually figure out what this converges to. I don't care. I'll just say by power test for integrals, this converges. Because again, the power is greater than 1 on that improper integral. I don't actually have to trade it out for limits because it was a very simple one. It really worked out nicely. So because that converges, and because we get to use the integral test, well, if the integral converges, the improper integral, then the series converges. So thus, the series from n equals 2 to infinity of 1 over n natural log squared of n converges by the integral test. It's a really nice test to use, but you can see there's a lot of conditions that you have to engage with, and there's a lot of like pre-work with this. And that's why I compare this to the by parts method, because in by parts there's a lot of little extra small bits that you deal with in by parts method for integration. Well, with convergence and divergence tests, same thing. Integral test is there's a lot of little parts to it. Okay. So questions on that? It's kind of a fun problem, honestly. Will there always be a test that we can, let's see, will there always be a test we can use, or could there be a time when no test can be used? Um, that would be cruel, right? I can't say that there's a test for every series out there. However, every series you're going to be handed, there's a test for. Yeah, how's that? So I don't want to give you something that's impossible for you to deal with. The vast majority of series that you're going to deal with, you will have a test that you can use. However, there are some very obscure series that you will not be able to find a test that works for, that will showcase any type of convergence or divergence. Um, so just know that there are just some unsolvable problems. This is how it is. That's a good question. All right, determine the convergence or divergence of the following series. Again, I'm not asking for you to tell me what it converges to, or if it converges, what does it converge to? I'm not asking that. I'm just saying, hey, is this convergent or divergent? Well, again, you should list out, maybe off to the side here, your methods. So far, is it geometric? And the answer to that is no. I suppose you could ask, is it telescoping? It's totally not telescoping, so I'm not going to bother with that. And can you use the divergence test? Is that a possibility? Well, that's a quick check. Most of the time, you don't even write this down, but I'm writing this down for your benefit so you could see kind of what your brain should be thinking about when somebody hands you a series like this. You should immediately, that first thing I do is divergence test in my head only. So if you were to use the divergence test here, you'd say, well, what about that limit as n goes to infinity of n e to the negative n squared? Now, because I'm not specifically saying, hey, use the divergence test here or something like that. You don't have to actually show me your work on this, but I'm telling you right now, this is 0. Limit as n goes to infinity of n over e to the n squared. That's terrible, n squared, by the way. It's a little bit better, I suppose. That is going to be 0. If you want to show that, you'd use L'Hopital's rule, but the reality is that is going to be 0. So the divergence test is not going to tell us anything. It's inconclusive. Okay. And there is a secondary question. If something is geometric, do both terms have to have the power of n, or do all terms have to have the power of n, or all factors? And the answer to that is yes. The only way for a series to be geometric is if it can be written like this. I'm waiting for me. There we go. That's the only way for it to be geometric. It might be n minus 1 or n plus 10 or something like that. But the reality is, if the only way it can be considered to be geometric is if everything is to that nth power, or n minus first power, or n plus 10th power, or n minus 14th power, or whatever it is. But most, like this series right here, not everything is written to the nth power. That first factor, n, is not to an nth power. Technically, nor is the second one. It's to the n squared power. So anyhow, so that being said, we're going to go ahead and see, can we apply the integral test? Well, to apply the integral test, again, we have to first create a function. That's kind of the easiest part. We're going to just let f of x equal x e to the negative x squared, or in other words, I like to write it this way, x over, well, no, I'll leave it that way. Actually, I think that's a good way to write that. So we'll start that. And then we just need to mention the 3 conditions. Is it continuous? Is it positive? Is it decreasing? It's continuous. I mean, there's not much I need to say. Some people will say, wait a second, that's going to be x over 1 over, it's x over e to the x squared. Well, still, that's continuous for actually all values of x. You try it out, but that's, if you wrote it this way, no matter what you plugged in for x, you're never going to have a division by 0. That's continuous. It's continuous everywhere. Also, it's positive. Notice how quickly I say that. Is it positive everywhere? No. But is it positive over the region that we're concerned with? No, actually, it's not. Initially, it's 0, right? So with n equals 0, yeah, okay, my function is 0 initially. So maybe I should say positive on 1 to infinity. Fine. Remember what I had said earlier about when you're using these tests is that I don't need it to always be positive. I need it to eventually always be positive. And this function is eventually always positive. Initially at time 0, no, it's 0, but eventually it's always positive. I hope that makes sense to you. The hardest part, which is not hard at all, is just seeing if it's decreasing. And so we just take the derivative. F prime of x is equal to. I'm going to actually use the product rule here because I hate the quotient rule. And so a derivative of the first is 1 times the second plus the first times the derivative of the second, which is going to be a negative 2x e to the negative x squared. Okay. And let's go ahead and clean this up because you'll never see if it's negative or positive if you don't clean this up. All right. And you still will not see it unless you clean this up. So let's go ahead and factor out e to the negative x squared. You should all know this. Exponential functions are always positive. That is a positive number there. Doesn't matter what I plug in, it's a positive number. Okay. So I know this is positive. That is eventually negative. Notice how I said that. It's eventually negative. In other words, our function's eventually decreasing. If you don't believe me, you could graph that. That is just an upside down parabola shifted up 1 unit. That's negative 2x squared plus 1. It is eventually negative. It's actually negative from 1 over the square root of 2 onward. So I'm going to say negative from, or I'll say on, 1 over root 2 to infinity. So again, I'm not really concerned about, oh, wait, initially that number is positive. I don't care about initial. What I care about is eventual. Eventually, that is going to be negative. And since I have a negative factor times a positive factor, I know that this derivative will be 0 for x in the interval 1 over root 2 to infinity. It's eventually decreasing is what I'm trying to say. So I know that f is eventually decreasing. It's kind of cool about this. It's almost like you're shooting off the hip a little bit, where you're just saying like, you know what, this function, it may not decrease initially, but eventually it's always decreasing. Eventually, right? And that's, I love series because of that, because we're not really concerned about the initial behavior. We're concerned with what happens over the long haul. All right, all 3 conditions are met: continuity, positivity, and the fact that our function is decreasing. So let's go ahead and use the integral test. All right, take a look at the integral. Let's see. I know it's going to be decreasing from 1 over root 2 to infinity. So let's just do the integral from 1 to infinity. That one is greater than 1 over root 2. So I'm just going to take a look at what happens with our function from 1 to infinity. Again, I could actually do this from 10 to infinity for all I care. It's not that big of a deal. You could throw out as many terms as you want. Okay. Again was x e to the negative x squared dx. I'm going to start by just doing a simple u sub. We'll let u equal x squared, so that du steals away 2x dx. This is kind of a nice substitution, because this will be the integral of, well, when x is 1, u is 1. Actually, I should write that. And when x goes off to infinity, well, so does u. And otherwise, let's see, I'm going to trade out an x dx for a 1/2 du, and then I have an e to the negative u. Now, this one, I do not have a theorem that allows me to say, oh, this converges immediately. I do have to actually evaluate this. So let's go ahead and do that. I don't need to figure out what the value is. I just need to make sure that it converges. So this is going to be the limit as t runs off to infinity of the integral from 1 to t, e to the negative u du. And we know the antiderivative. It's one of our favorite integrals, right? So limit t runs off to infinity of a negative e to the negative u from 1 to t. And I'll go ahead and factor out the negative. I really hate negatives within my evaluation, so I'm going to throw that out front. And now I have e to the negative t minus e to the negative 1. But remember, e to the negative t is just 1 over t, e to the t. And this will tend, as t goes to infinity, that will tend to 0. And so this is going to be 1 over 2e. Just letting you know, just because that is 1 over 2e does not mean our series becomes 1 over 2e. All I really care about is it converges. So this implies convergence of integral. But because the integral converges, the improper integral, that implies that our original series must converge as well by the integral test. So there we go. I'm going to go ahead and write that down. That implies the series converges by the integral test. So that's a really nice, again, a very, very nice problem. And I think, I think what I want to do, because if I go any further, I'm going to get into bigger problems. And because we're going to have a week off, I want to be able to start back on that Monday and kind of remind you. And the next theorem that I'm going to touch upon will actually be useful for reminding you of all of this conversation. So strangely enough, we are going to stop here. One thing I do want to show you, though, before I let you go, is that from this point forward, every time we complete a section, you'll see the last page of the section we complete has a summary of, give it a moment because my screen has to catch up to me. There we go. The last page of every lecture or section that we go through is going to have a summary of what we've learned so far. So if you look on My Open Math and look at my lecture notes, you'll see the end of the section tells us, hey, what are our methods so far for testing for divergence? And what are our methods so far for testing for convergence? And every time that we go through a new section, I'm going to build on to that. So even right now, this should be okay for you because we've actually already introduced all this information. So right now, these are the tools at your disposal. So anyhow, I think it's a good time to stop. I know we're stopping 10 minutes early. I know you're upset about that. I totally get it. But honestly, spring break, go have fun, or have fun, but be careful. All right. Everybody have a wonderful spring break. Remember, I don't have office hours today because I have to rush off someplace. So you guys have a wonderful, wonderful spring break. I'll see you on the Monday after, and we'll hop right back into this. Okay. All right, you guys Have a wonderful spring break. I'll try to check emails and stuff like that as I can so that I can answer questions. Otherwise, take care, everybody. All right. Bye bye.